One, two, three. One, two. One, two.
That's the one built into the room. Same as yours, I think.
Yeah. Oh, whoops, I forgot to. Can you guys hear me up there? Are we good? Can everybody hear me? No? How about now? Is this better? Oh, it's too loud. How about this? Good? All right. So Nathan asked me to talk about research, and my research involves algorithms. And that pretty much covers everything. Everything is an algorithm, right? I keep saying all of life is one big set of algorithms and heuristics. So in algorithms, just like in many other areas, you want to try to simplify things. Einstein famously said, make everything as simple as possible, but not simpler. So there's Einstein simplified. And in algorithms, you can go for exact solutions, but those typically take too long for intractable problems, NP-complete problems. We talked about that a lot in theory. How many here are in my theory course? Okay, so you know all about NP-completeness. So we just go for quick and dirty heuristics. We try to avoid local minima, getting trapped in local minima, and the solution spaces are very complex. We try to find global optimum whenever we can muster that. And one of my main areas in the 90s and 2000s was VLSI design. It's just ripe with lots of optimization problems, including Steiner trees and placement and routing. But basically, you try to take some real-world requirement, like the need to communicate securely, say, and then you come up with some data encryption standards, some design specification in general, from which you come up with a functional design. It could be consisting of formulas and very specific protocols and algorithms. Then you implement that in silicon, in logic, using Boolean formulas and OR and NOT gates through a structural design phase. From an available library of subroutines, you try to implement your logical design as some structural design. Then you need to lay it out in physical silicon. That's called the physical layout stage. And then, of course, you fabricate the chips, and you get microprocessors out of them, which you package, and then you put in workstations. And a lot of the heavy lifting, algorithmically speaking, happens in the physical design or physical layout stage. We have hundreds of different intractable problems with varying optimization constraints. Sometimes it's multiple constraints of optimization working at odds with each other, involving many trade-offs. So one classical problem in chip design is placement. Where do you place all your components, whether they're transistors or chips or memories, capacitors, resistors, other components, whatever those may be, ALUs, such that when you interconnect a bunch of pins which are supposed to be electrically equivalent, i.e. connected to each other, how do you connect them using some routing in some best way? And best can vary in terms of definition. Typically, we talk about minimizing wire length in the old days, but nowadays, it's not just so much the wire length, but signal propagation delays dominate, and sometimes it's multiple constraints. And so very long time ago, in the late 80s, early 90s, I made an observation, and I wasn't the only one, but I saw that transistors are getting smaller and components are getting tinier in general and cheaper. And to a first order approximation, they just vanish to points. But the interconnect between them doesn't vanish. It just stays pretty much invariant. When you want to interconnect two computers across campus or across a city or across the nation or across the planet, these computers are getting cheaper, smaller, faster, tinier, but the fiber optic between them is still expensive, and it's still not cheap to dig up ground and bury fiber optics or create any other communication networks. That's expensive in terms of capital, effort, size, and so on. So to a first order approximation, the system becomes just a network. The things that the network connects to each other are almost irrelevant in terms of size and cost and so on. So you end up with nothing but net after a while. So that's a general trend, and not just in microprocessors, but in other things too. So that gives rise to the famous Steiner problem. It's a classical problem. How do you interconnect a bunch of points to minimize the total wire length or interconnect length between them? And of course, you can use a minimum spanning tree. So if the 3 points lie on the corners of the equilateral triangle, it takes 2 units of wire to connect them. But if you add one more point in the middle, the interconnect length can drop substantially. So if you add a point there in the center, the total wire length now becomes square root of 3, as opposed to 2 units. Square root of 3 is roughly 15% smaller than 2. It's about 1.7 something. Now this example is trivial, but if I give you a non-trivial example, like here are a bunch of points I'm trying to interconnect, and you need to pick the red points that could be used as junctures, where do you put them, and what does the topology look like? And that problem is NP-hard. It's very difficult to solve in an exact way. So for this example, you want to put the intermediary points where the red dots are, and your overall topology looks like this. But it's not at all obvious for any given point set. And by the way, all the wires are straight lines here because we're using the Manhattan metric. Delta x plus delta y is the distance between 2 points. But you can use any metric you want, and it's still a metric space, and you can have instances where triangle inequality holds, which makes it easier to solve. It's still NP-complete, even with triangle inequality, but it makes it easier. So here's a simple heuristic for this problem. If you were only allowed to use one red point, not many, but just one, where would you add it? So here is a bunch of points, 4 points in blue. Where would you add a single red point to minimize the overall minimum spanning tree length of the original green points plus this single red point P? So here's a minimum spanning tree. Again, lines are rectilinear, so don't let it worry you that you can make this problem in any metric or even in any dimension that you'd like. But if you can only add one point, you may want to add it right there so that the new minimum spanning tree over the green points plus the red points drops somewhat to this configuration and save you some wire length. And then you just repeat this, right? One of the beautiful things about computers, they can do things repetitiously. So another point next might be right there, and that drops the MST cost, the minimum spanning tree cost, to that. And it turns out for this example, this is optimal. But in general, this heuristic works really, really well. For 4 points, it gives you the optimal solution. That's not trivial because there were literally hundreds of heuristics for this problem over the years. But many of those did not give you the optimal solution even for 4 points. And of course, in general, we don't know what the optimal is in polynomial time because it's NP-hard. Another thing that you can prove about this heuristic is that it's no worse than 3 halves optimal, 1.5 times optimal, 50% more than the optimal, guaranteed, no worse than that. Even though we can't compute the optimal in polynomial time. And then for special difficult point sets, it's no worse than 4/3 optimal. It turns out you can prove all these theorems. I proved all these theorems in various papers I've written. And on average, it's nowhere near 3 halves optimal. It's no worse than roughly 0.5% away from optimal. And in the theory course, we talked about how NP-complete problems, even though they're intractable, and even though there's heuristics for them that are no worse than twice optimal, some constant times optimal, on average, you're nowhere near that pessimistic upper bound. It's just a guarantee that you'll never be worse than that. But it's actually hard to find instances where it's as bad as that bound. And certainly here it's true in spades. So no worse than 0.5% times optimal, which means it's just a sliver away from optimal on average. And this heuristic outperformed all previous heuristics for the Steiner tree problem. It works really nicely. Another variation of the Steiner problem, the group Steiner problem. So here, you want to pick 1 point from every group. 1 point from the greens, 1 point from the blues, 1 point from every color, and interconnect those. And you have this now extra parameter of flexibility or dimension of optimization that you get to pick which points you want to connect as long as it's 1 from every colored group. So here, if you pick these 3 points circled in purple and interconnect them like this, that's a pretty long tree. But on the other hand, if you pick another set of 3 points from the 3 different colors, you can interconnect them with a much shorter overall tree. And that's called the group Steiner problem, where you want to interconnect 1 point from every group to all the other points, 1 per group. Of course, this version of the problem is interesting in another way because the optimal solution can be a forest, not just a tree. So for example, if you interconnect the purple to the green, then you can pick another point from the green to interconnect to the purple. Now you have a forest solution rather than just a single tree. Of course, a tree is a forest with just a single tree in it, but more generally, you can have many trees. So it turns out that's NP-hard, not surprisingly. You know, if a problem is hard, any more generalized variation of it is even harder. It's not any easier. And this is a hard problem because the classical Steiner problem is a special case where every group is of size 1, and so you have no choice of what to pick. You're forced to pick that point specifically. It turns out it's even hard to approximate. It turns out that any smaller approximation bound than the logarithmic of the number of the groups, that's NP-hard also. So it's not just NP-hard to get an exact solution. It's actually NP-hard to even approximate it, not just within a constant factor, but within a log factor of the number of groups. So it's like doubly or triply hard in that sense, because many NP-complete problems are hard enough, but you can approximate some of them to any degree of closeness to optimal, like epsilon within optimal. But this one, not even close. But I had a heuristic that gives you a solution guaranteed to be within the number of groups raised to some epsilon power, any small power of the number of groups, however small, like square root, cube root, 10th root. So not quite log, but arbitrarily close to log, still being a low degree polynomial times optimal. So, and that of course runs in polynomial time. All these heuristics better run in polynomial time, because if you're allowed exponential time, might as well solve it exactly and dispense with the trickery of heuristics and approximation schemes. So the graph Steiner problem, it's even a more general version of the Steiner problem, where you have a graph and all the edge weights are arbitrary, and you have to connect a bunch of points. All the points in blue need to be connected to each other, and the other points that you're not designating as blue ones may or may not be used in the solution, your choice. So you have options on the red points. But if you use the red points, they better be used in a way that saves. And the question is, what's the overall topology? So in this graph here, where you have to connect all the blue points and optionally throw in some red points at your discretion, these are the Steiner points, a solution might look like this. The red spanning tree here spans all the blue ones and some of the red ones. And the question is, what's the shortest tree that you can create in this way? And that's even harder than the geometric Steiner problem, which is a special case of it, where the distances are all geometric distances induced by the locations of the points in the plane. So I had a heuristic that's no worse than roughly 1.55 times optimal, and it's even better than that in specific families of graphs, and it's held the world record for the best bound for the Steiner problem for about a decade, won a Best Paper award. I think more recently somebody beat that, but it held the world record for 10 years, so that's pretty good. Bounded radius trees. Here you want to interconnect a bunch of things, but you want to minimize the radius of the tree, the total node-to-node maximum distance within the tree. So for example, if you didn't care about the radius, a minimum spanning tree is always the best interconnectivity of a tree. That's why it's called minimum spanning tree. Prim, Kruskal, very fast algorithms for minimum spanning trees are known, low order polynomial time. So this is like Prim or Kruskal. This will get you a minimum spanning tree. But the distance from certain nodes to certain other nodes will be very, very large in this tree. And if this tree is a communication network, or say a clock network on a chip, where the clock source propagates in the middle, and all these are clock sinks we have to deliver the clock signal to, the clock signal will take forever to propagate across that chip like that, given this topology. And by forever, I mean many nanoseconds. And on a chip, nanoseconds is way too slow. These chips run at megahertz, at gigahertz speeds, 3-4 gigahertz nowadays. And light only travels a foot per nanosecond. So, if you talk about a 3 gigahertz processor, every clock cycle, the speed of light is only 4 inches across. So between successive additions or multiplications of this chip, light only can travel 4 inches. So that's very, very tight timing conditions. So every picosecond counts now. So you may want to say, okay, let's connect the tree's nodes like that, like a bicycle spokes of a wheel. But if you could connect everything to the central, say, clock signal generator like this, using this bicycle wheel topology, yeah, you'll have short path lengths from the source to all the sinks. But the problem is you'll have a lot of wire and a lot of total wire length, and wires are metallic, and metal is essentially capacitance and resistance. You have plenty of capacitance here, and capacitance will slow you down. You have to charge up all this massive metal high and low, electrically speaking, billions of times a second. And if you have too much metal, this is not going to happen. It takes too long to charge up a larger mass, and it acts as a higher capacitor. So, these are parasitic effects that go against speed. So you may want to use this hybrid topology instead. Not a bicycle wheel and not a long path around the periphery, but a few short groups around the periphery like this, and then within that, connect each group in turn to the central node, and that's a much more reasonable topology. It's a trade-off between high cost of interconnect and low speed of, say, Dijkstra's kind of shortest paths tree, which will be the bicycle spokes kind of topology that we saw earlier. And the question is, how do you achieve this in general? So I have algorithms that, for any epsilon that you choose, will give you a tree that has radius no worse than 1 plus epsilon times the optimal, and will have cost no worse than 1 over 2 over epsilon, 1 plus 2 over epsilon times the optimal in terms of the cost simultaneously for the same tree, which is great because you're bounding now 2 quantities simultaneously. It's hard enough to bound 1 quantity, like cost or radius, right? But it's very hard to bound 2 quantities simultaneously, especially since they're mutually competing. This tree here has very good radius, the best radius, in fact, 1 unit if it's a circle of unit radius, but it has terrible cost. This tree before that we saw has great cost because it's a minimum spanning tree, the best tree possible, but it has terrible radius, long meandering path, unnecessarily long. So this shows that it's competing objectives. Anyway, other problems I looked at, again, they're all connectivity problems because remember we talked about connectivity being a very ubiquitous problem. Every time you want to interconnect something, whether it's on a chip or in this building, the ducts, the water pipes, the electric conduits, these are all connectivity networks. Even the blood vessels inside your body are a connectivity network, conveying blood to cells and so on. Connectivity is a very ubiquitous problem at every level of abstraction, at every level of granularity. So low degree minimum spanning trees, again, rectilinear metric here. Minimum spanning tree on these 5 points look like this. No big surprise. If you throw in these extra points, the minimum spanning tree basically looks like this. But now you have a node of very high degree in the middle, degree 8. And that's not great. The higher the maximum degree of a tree, the more contention you have in lots of connections trying to reach the same point and so on. I mean, imagine if all the electrical, high voltage wires in your city from every neighborhood try to connect to the same power station or the same transformer. There'll be thousands of wires trying to get to the same tiny space, and it just won't happen. So you want to minimize the maximum degree of a tree, typically. It turns out for this example, the cost is 8, and the maximum degree is also 8 in the middle there. But you can come up with this topology, which reduces the maximum degree to only 4, and the cost remains 8. Remember, this is the Euclidean metric now. So that's a much better tree. And in general, I proved some theorems that the maximum degree 4 is always achievable in the plane in the Manhattan metric. Before that, these problems were not known. The maximum degree of 14 is always achievable in 3 dimensions. The best previous bound for that was something like, 26 or some very large number, much larger than 14. You can show that there's a lower bound. I showed there's a lower, this max degree can never be less than 13. So I just have an example. I found an example, counterexample where a degree of 13 is forced for the minimum spanning tree. No spanning tree has, there's an example of a few dozen points that no spanning tree whatsoever has, no minimum spanning tree, I should say, has degree less than 13. And I showed an upper bound of 14. So the question of whether the real bound is 13 or 14 is still open after all these years. So that's one of many open problems that are involved in this area. But before you all rush to try to solve it, let's just say I tried, I couldn't. That doesn't mean you can't, but it's a very tough problem. Probably worth a PhD in of itself, I would say. Low skew trees. So sometimes you want to deliver clock signals to a bunch of points and create not so much the lowest minimum interconnectivity length, but the lowest skew in the interconnect. In other words, the smallest difference in path lengths from the source to all the sinks. So in clock tree distribution on chips, that's exactly what you want, low skew. Ideally, you want zero skew. You want the signal to arrive as simultaneously as possible to all of its destinations. Even in real life, in the macro level, like when, I don't know, the New York Stock Exchange publishes stock prices of varying commodities and stocks to the rest of the world, they don't want to publish necessarily the prices to one particular area a lot earlier than other areas, because it puts people there at a disadvantage in the slow areas and people in the fast areas of distribution of stock prices or whatever at an advantage, and that can create huge financial disparities. In fact, there's a whole area in finance called high-frequency trading that leverages on exactly that. And we're not talking about seconds of delay. We're talking about milliseconds or microseconds of delay in knowing the prices or the occurrence of transactions onto the market. And some people can use those few microseconds to quickly put in certain buys and sells and make millions of dollars a day if they're rolling around billions of dollars. How many heard of that, high-frequency trade? So this is another example of where you want the skew to be minimized. You want people to get that information as simultaneously as possible and not give anybody an advantage. Well, so you can do minimum matching on these target sinks that you want to interconnect, then connect the midpoints together, do a minimum matching on the midpoints, and recursively do a minimum matching on the midpoints of the midpoints, and so on. And finally, you have a single edge on the midpoints of the two remaining trees, and the whole topology now is one big H-tree generalization. And that creates very low skew kind of topologies that are great for clock distribution on chips and other information delivery networks and so on. And by the way, in the real world, when you talk about networks, the physical topology doesn't have to look like this. The logical topology can look like this, superposed and overlaid over an actual physical topology. So this doesn't mean the real network has to look like this, but logically it does. It can be implemented this way. Another problem I looked at over the years is circuit testing. You have a circuit coming off the assembly line, like a motherboard or some PCB, printed circuit board, and you want to make sure that all the wires are there and there's no shorts, no cuts across wires that are engineering or production mistakes. Because if the circuit board is not functional, if there's cuts in any of the wires, you don't want to start putting chips on them, solder chips onto the board, because if you then test it and see that the board is not working correctly, never mind the chips, then you have to throw the whole thing out. You can unsolder them and reuse those parts. They're very sensitive and delicate, and every tiny little sliver of solder counts in terms of capacitance and resistance and slowing you down. So you want to test these circuit boards, and by testing them, you can put mechanical probes in 2 points on a circuit board and test that the entire path between them doesn't have any shorts or cuts in it. I guess I should say open faults. These are cuts. Shorts are when things are connected together inadvertently. Open is when they're not connected when they should be. So if you touch A and B with mechanical electrical probes, you'll test the red path between A and B, but that doesn't test the rest of the tree. So the question is, what's the minimum number of probes you need to put on a tree, and in order to test the entire tree, the entire interconnectivity of this tree-like structure? And I have algorithms that give you the least possible number of interconnect probes that you need to do to completely test the tree. It turns out it's a number of leafs over 2. Those are necessary and sufficient. To see that they're necessary is not hard, actually, because if there's any leaf that you don't touch using one of your probing pairs, the edge right next to that leaf that you didn't touch will never be tested. How many can see that? So it's easy to see. It's not so easy at all to see that leafs over 2 are also sufficient. That they're necessary is trivial. If they're sufficient, that's not trivial at all. So we prove that, and we have an algorithm that finds this best possible number of probes, leafs over 2, ceiling of the leafs over 2, because it could be a fraction. And that algorithm finds that optimal solution in optimal time. So this algorithm is doubly optimal. Again, that's hard to do. It's easy to come up with an optimal algorithm in time that doesn't give you an optimal solution with respect to accuracy, or vice versa. An algorithm gives you a very exact solution, but takes forever to run. In fact, if you spend exponential time, you can do that trick for any problem in NP. Take exponential time to run, and you'll get your exact answer. The algorithm, though, will not be optimal and will not even be polynomial time. So this one runs in linear time and gives you the best solution possible. When you manufacture chips, if there's any areas that have varying density compared to another area, it reduces the yield, it turns out. There's a step in chip manufacturing called chemical mechanical polishing, where you literally mechanically polish the chip after laying metal on the silicon, and then you lay another layer on top of that, and you polish that so that artifacts like mountains and valleys on the chip don't interfere with the next layer and the next layer, because these errors compound when you keep layering more and more etching components and layers and transistors and wires onto the chip. Chips typically have dozens and dozens of layers of tiny little micro wires. The width of those wires is hundreds of times narrower than the human hair. Really, really tiny. You can barely see them even under a microscope. You know, the size is nowadays the size of the width of these wires is measured in nanometers, like 10 or 12 or 15 nanometers. That's it. So you need to create a way to make the density uniform by adding potentially kind of dummy features that don't do anything electrically, but they serve to make the surface as uniform density as possible, so that when you polish them, no areas get over-polished because they have very much lower density than the other areas, which resist the polishing kind of mechanical process by being more dense. So anyway, we have some great algorithms for that. And an entire startup company was founded on the basis of this piece of research called Blaze DFM back in the mid-2000, 2005 or so, and then it was purchased by some other company. I didn't get any stock in it, though. They just used my algorithms. But that's good enough for me. You know, when industry uses your algorithms, that's a good thing. It's a good day. Landmine detection is another interesting algorithmic problem. It turns out that militaries put landmines in the ground in equally spaced collinear rows. And the reason they do that is so that after the battle, which they assume they'll win, they'll be able to take them out of the ground because they'll have a better idea where the mines are. And both sides do that because both sides of the conflict assume they'll win. Usually one of them is very wrong about that assumption. But you know, if they knew that ahead of time, they probably wouldn't enter into the conflict. So you know, kind of stands to reason that both are pretty sure they'll win at the beginning. So where are the equally spaced collinear mines? You take infrared pictures from a plane, and various objects come out as dots in infrared imagery. And these dots could be mines, landmines, or they can be rocks or frogs or other objects, fence posts. You know, this is from vertical vantage point. So, but rocks and frogs don't sit in equally spaced collinear subsets like these points on this line, but unless it's a Budweiser commercial. But mines tend to, and so these are potential mine locations. By the way, landmines are a huge problem in real life. There's about 100 million landmines all over the planet in the ground waiting to explode, live mines. Usually the people who get hurt from mines are children. Mines are not designed to kill soldiers, actually. In military euphemism, mines are referred to as area denial weapon, or area denial device, rather, even, not even a weapon. It's designed to deny your adversary use of this area. If they know there's mines there, they're not going to go in, they're go around. So it's used to restrict area of movements or force your adversary to take long routes, meandering routes where you can maybe lay ambushes or force them to go where they don't want to go. So it's not designed to kill, it's designed to, at best, maim people. So mines tend to be like low yield kind of explosives that are designed to take out a leg or an arm, but not even kill a person. Again, the idea being that if you can disable a soldier in your adversary's army, that puts out several other people out of commission in that same army because they have to tend to that person, paramedics, ambulance drivers, and so on, helicopter pilots who are extracting them into hospitals, and those are out of the fight now. So you don't actually want to kill, you want to maim. This is all very sad, but this is just what happens, just so you know. So landmine extraction and detection is a huge problem. The cost of putting a mine in the ground is only a few pennies, like a dime or a nickel, roughly. It could be very small, like the size of buttons. The cost of extracting a mine out of the ground is about $1,000. And the reason this disparity between insertion and extraction of mine in price is the medical bills of all the people who are trying to get mines out, and eventually they get hurt, and all sorts of medical bills or funeral bills or whatever. So it's a very, very tough problem. Most of these mines will never be extracted, sadly enough. Anyway, so if I say there's another subset here that's equally spaced and collinear, where would you say it is? It's hard to tell because the human eye, has trouble seeing these kind of patterns. Even algorithms have a hard time seeing these kind of patterns. But maybe this one, equally spaced and collinear, that's another mine potential locations. And so I have an algorithm that does it relatively efficiently. And then Nathan actually did some follow-up work about compression that uses this in other contexts to compress point sets and then operate on them and so on. It has interesting applications, these kind of techniques and algorithms and insights. The US military actually used this algorithm this is back in the 90s. They used to have much slower kind of, may say, n-cube time algorithms to detect potential landmine locations and images, and it ran in like hours and hours per image. And of course, you got thousands of images coming in per minute from satellites and planes. So those took too long. And when they ran my algorithm, it just took a few seconds instead of hours. So they were flabbergasted. Of course, stands to reason because this is asymptotically faster. This is like n squared versus n cubed, what they were running before. And you can't fight intractability by throwing silicon at it. You have to, ideally, you want to be algorithmically clever or resourceful, not just blindly throw silicon or extra processors at the problem. That'll get it a little faster too. But if you're algorithmically resourceful and MacGyverish about how you design the algorithm, you can still use multiple processors and the whole thing will run even faster yet. The speed of the processors will amplify the speed of your algorithm, so it's the best of both worlds. So that's what you want to do. Don't just parallelize things as a first resort. Think about the underlying algorithm, and do what you can there too, because those are easier wins than commandeering a lot of silicon, like an entire cloud computing platform or whatever. Okay, I mentioned moving target TSP, I think in a theory course. Here's more details. So it's TSP, except classically TSP, traveling salesman tours. The points are stationary. They can't move. Here, every point has a vector associated with it. So for this particular example of 4 points, the vectors show how fast they're moving and in what direction they're moving. So they look like this. They're continuously moving. Want to see it again in instant replay? There we go. Okay. So the question is, starting at the origin, where would you go to pick up the first point, second point, third point, so that you can pick up all the points and return to the origin, given that they're not moving, they're not stationary. Now, even if they weren't moving, this is still classical TSP. It's NP hard, it's intractable, there's lots of heuristics. We don't know how to solve it exactly. If they're moving, you can forget about it. That's even worse. So we have some heuristics, and one problem when you chase these points is that you can't even go to where the point is now. You have to go to where the point will be by the time you get there. So you have to kind of be indirect about it. Even when you try to find one point, it's not trivial to compute where you need to head head it off at the pass. So for example, you want to pick up the first point there, it's the same vectors as before. The next point, by the time you get there, it would have moved. The third point, by the time you get there, it would have moved again, quite a bit actually. And the fourth point, by the time you get there, it would have moved yet one more time, and then you return to origin. And the tour can self-intersect. It's one of the big differences between moving target TSP and classical TSP. Classical TSP, if you have a self-intersecting tour, it can't possibly be optimal by the triangle inequality, right? How many remember that discussion from? Good. Just testing. So here, the optimal tour can self-intersect. It's another complication, of the moving target TSP. It can happen. And not only that, in one dimension, classical TSP in one dimension, where all the points are on the line, that's trivial. You pick up all the points to the left, all the points to the right, that's your tour. In this scenario, even the one-dimensional problem is not obvious at all, because you can have points moving very, very close to you, moving at the speed of light in both directions. And the other points are very slow. So if you go to one side and pick up all the points on one side and all the points on the other side later, by the time you get to the other side, that other point on the other side of you that's moving at the speed of light away from you will be in the next galaxy. So what you want to do is pick up the fast point here and then a fast point there, and then go to slower points, and there's a whole number of levels of this kind of optimizations you can do. Anyway, we have exact algorithms for the 1D version, which is unusual. So it's an NP-complete problem, but in 1D it turns out it's not NP-complete. Well, it's polynomially solvable, and And we can solve it exactly. I see some restlessness. Are we done with time, or how are we doing on time? Oh, 1 minute, okay. So we've solved problems on minimum surfaces, evolutionary trees, where you want to arrange taxa.
By the way, this chatting is very rude. Thank you.
All right. I'll try to finish, in a minute. So you want to arrange taxa species in an evolutionary tree that relates closely related taxa or species evolutionarily to be close in the tree. So to me, it's just another tree connectivity problem. And we did some work in computational biology, polymerase chain reaction experiment, PCR experiments, where you try to find good primers that can identify unknown proteins. So we have algorithms that can help biochemists and biologists identify new proteins. So that's pretty cool. It's hard to isolate and identify new proteins. If you have an algorithm to help do that, that's nice. And then we did some work on tiling microarrays, basically computational biology, genomics. We have a paper in Science regarding our efforts in the encyclopedia of human genome elements. And we did some work on RFID, radio frequency identification, trying to use RFID tags as indoor GPS localization kind of technique. We pioneered the notion of putting multiple tags on objects, multiple RFID tags. It turns out it increases their visibility and decreases the glitches that RFID tags cause in terms of misidentification and so on quite substantially. So lots and lots of problems. They're all algorithmic, and we just love solving problems as best we can, and it's all very exciting. Cuts across all fields, algorithms do. All right? Any questions? All righty then. So we'll see you around. Thank you.
Require that, well, sorry, let me